Hello everyone, welcome to the solution of assignment number 3 on network analysis. In this video, we are going to see some numerical related to the network analysis based on the network theorems. In the first problem, it is given that this is one voltage source and the current flowing through that voltage source is given. Voltage is given as 50 at an angle of 30 and the current is given as 27.9 at an angle of 57.8 degree. We have to calculate the value of this impedance such that this current is equal to this value when voltage is equal to 50 at an angle of 30. So see here, it is clearly observable that these three branches are in parallel. So this is the parallel circuit problem. So let us assume that this ZA impedance is equal to Z ohm, ZB impedance is equal to 5 ohm, and ZC is the combination of 3 minus J4. These two are in series, so 3 minus J4 ohm. So how will calculate the equivalent impedance in parallel circuit? 1 upon Z equivalent is equal to 1 upon ZA plus 1 upon ZB plus 1 upon ZC. That is equal to 1 upon Z plus 1 upon 5 plus 1 upon 3 minus J4. We will keep as it is. How we will calculate the Z equivalent? Z equivalent is equal to V upon I. So V phasor upon I phasor, 50 at an angle of 30 divided by 27.9 at an angle of 57.8. So we will getting this Z equivalent is equal to 1.792 at an angle of 27.8 ohm. So I will substitute this Z equivalent value in this equation. So 1 upon Z equivalent is equal to 1 upon Z plus 1 upon 5 plus 1 upon 3 minus J4. After solving this, I am getting 1 upon Z is equal to 0.2 at an angle of 30. 0.2 at an angle of 30. That is Z is equal to 5 at an angle of minus 30 ohm. So one upon Z is equal to nothing but a ZA. So ZA is equal to Z. So 1 upon Z, taking the inverse, Z is equal to 5 at an angle of minus 30 ohm. Okay, so now let's solve the next problem. Obtain the Thevenin's and Norton's equivalent circuit in the terminal A, B. Okay, so terminal AB is given, and in between these two terminals we have to obtain the Norton's equivalent circuit and Thevenin's equivalent circuit. So we know that the Thevenin's equivalent resistance and Norton's equivalent resistance, the Thevenin's equivalent impedance and Norton's equivalent impedance are same, they are not different. So first we'll calculate the Thevenin's equivalent impedance, that is Norton's equivalent impedance. So to calculate the Norton's equivalent impedance, we have to, or Thevenin's equivalent impedance, we have to shorted this voltage source. As internal impedance is not given, we will replace this voltage source by short circuit. We will replace this voltage source by a short link. So looking from the AB terminal, we have to calculate the ZTH. Looking from the A to B terminal, it is clearly observable that these two combinations are in parallel. Okay, so these two combinations are in parallel, whereas these two combinations are in parallel in series with the 5 ohm resistance. So 10 into 3 minus J4 divided by 10 plus 3 minus J4 plus 5, this will give you total Z equivalent, that is ZTH, between the A to B terminal, that is 8.86 at an angle of minus 15.17 ohm. Now here there are two approaches to calculate the Thevenin's equivalent voltage. I am going to calculate the Thevenin's equivalent voltage based on the KVL KCL law. So now let us consider that this AB, I'm showing the ZTH AB in this, between these two terminal. Let us consider this VTH is not there. If this VTH is not there, what is the current through this path? What is the current through this path when VAB is not there? Current through this path is equal to 0. Means in this section the current is equal to 0 if the VTH is not present. So we have to calculate the VTH value such that the current flowing through this is equal to 0 and I1 is equal to, and in this is the current I1. So applying the KVL loop, applying the KVL in the first loop and second loop. So what is the total impedance in the first loop? 3 plus 10 minus J4. So 3 plus 10 minus J4. So 3 minus J4 I1 plus 10 I1 and I2 is equal to 0. So I am getting I1 is equal to, so I am getting the value of I1 is equal to minus 20 upon 0. Why it is minus 20? Because it is indicating the minus side. So minus 20 at an angle of 0 divided by 13 minus J4. So the current is 1.147 at an angle of minus 162.89 ampere. Okay, once the I1 current is determined, now applying the KVL in the second loop. So if we apply the KVL into the second loop, 10. So what is the current flowing through this 10? It is I2 minus I1. 10 I2 minus I1 is equal to, what is the current flowing through this? Current flowing through this is equal to 20 at an angle of 0. 20 at an angle of 0, because it is indicating plus sign. Then here it is indicating minus sign. This arrow is indicating minus sign. This is minus 10 at an angle of 45. Again we are traveling from A to B. Again it is indicating minus sign, so it is a minus VTH. Why I have not considered 5? Because no current is flowing through the 5, because I2 is equal to 0. So substituting all these values, so we will get the value of VTH as 11.45 at an angle of minus 95.61 volt. So what is the Thevenin's equivalent circuit? Thevenin's equivalent circuit is a voltage source behind the Thevenin's equivalent impedance. So voltage source is equal to 11.45 at an angle of minus 95.61 volt, and ZTH, which we have calculated here, 8.26 at an angle of minus 15.17. This is the Thevenin's equivalent circuit. How will you calculate the Norton's equivalent circuit? To calculate the Norton's equivalent circuit, we have to shorted this link. So if we short this link, so this I2 current is now not 0. So I2 current is significant. I2 current will be there. So applying the KVL between loop 1 and loop 2. So I will get the first equation, 10 plus 3, 13 minus J4 I1. 10 is the common in between these two. So I1 and I2 are in opposite direction. So it is a minus 10 I2 is equal to, this arrow is indicating minus 20. So it is a minus 20. Similarly, in the second equation, I1 and I2 in opposite direction. So it is a minus 10 I1. 10 plus 5, 15 I2 is equal to, this arrow is indicating plus, so plus 20 minus, because this is indicating minus, so minus 10 rectangle. So after solving these two equations, I am getting the current I2, that is the Norton's equivalent current, is equal to 1.39 at an angle of 80 degree ampere. So this is the Norton's equivalent circuit. In Norton's equivalent circuit, IN is equal to 1.39 at an angle of 80 ampere, whereas in parallel with the ZTH, or you can say it is a Norton impedance also, Zn or ZTH, 8.26 at an angle of 15.17 ohm. This is the one approach. By using the KVL and KCL law also we can solve the Thevenin's equivalent problems and Norton's equivalent problem. Second problem we will solve here based on the circuit reduction. Okay, so in this we have to calculate the Norton's equivalent circuit and Thevenin's equivalent circuit between terminal A and B. So I will redraw this circuit. So I will expand this path outside. So if I extend this path outside, the A and B terminal, I can brought it outside. So this circuit can be redrawn as 10 in series with the 10 at an angle of 0 source, 4 plus J4 in series with minus J10. So we have to calculate the Z equivalent looking from these terminals. We have to consider these as a shorted. So these two will come in parallel in series with this. So 10 at 10 into 3 plus J4, 10 into 3 plus J4 divided by 10 plus 3 plus J4 plus minus J10. It will give you 8.38 at an angle of minus 69.23 looking from A to B terminal. How to calculate the VTH? To calculate the VTH, so keep in mind, as the current is not flowing, no voltage drop across this, means whatever the voltage drop across these two element is nothing but the voltage across AB. So VTH is equal to VAB voltage, that is voltage drop across 3 plus J4 ohm. So I will calculate the voltage drop across 3 plus J4 ohm by using the voltage divider rule. 3 plus J4 divided by, these two are in series, these are in series. If this is not carrying any current, these all in series. So 10 plus 3 plus J4 into 10 at an angle of 0. This is using the voltage divider rule. Using the voltage divider rule, I am getting VTH is equal to 3.67 at an angle of 36.03 volt. So this is the representation of VTH and ZTH. Similarly, how will calculate the Norton's equivalent circuit? To calculate the Norton's equivalent circuit, first I will calculate the Z equivalent. Z equivalent is equal to, so how will calculate the Z equivalent? These two will come in parallel now, because this is shorted now, hence the current supplied by this is divided here and again meeting back here. So this branch and this branch is in parallel. So minus J10 is in parallel with 3 plus J4. So minus J10 is parallel with 3 plus J4. Considering this, and adding this plus 10 we'll get the Z equivalent. How will calculate the current? Current is equal to voltage divided by Z equivalent. So I is equal to 10 divided by Z equivalent. I'm getting this value. So to calculate the IN, I can use the current divider rule. So this branch should be taken in the numerator divided by sum of this. So 3 plus J4 divided by 3 plus J4 minus J10 into the total current is taken. So it will give you the Norton's equivalent current as, that is the current flowing through this J10, 0.438 at an angle of 105.27 ampere. These two approaches can be used for the solution of network analysis problem. Thank you.